Thanks everyone for joining. We'll just wait an extra minute or so as people arrive. Great. Thanks everyone for joining for the Rocky Worlds discussions meeting today, 2nd of May 2024. Just a reminder how the format of the meeting is going to work. We'll have a talk, 30, 40 minutes or so, and then an open discussion at the end. So think of questions during the talk, and we'd love to get the conversation going afterwards on what's going to be a really exciting topic today. And then we'll aim to finish kind of strictly on the hour. So hopefully there's later discussion, and I'll apologize in advance if we need to cut that short just to keep everyone kind of leaving the meeting when they need to get on to their next commitments. Just a kind of netiquette point, and I see immediately I'm in violation of this, so apologies. I was trying to update my name and forgot to get it finished before the meeting started. Please use your full name. I'm Ollie Shortall. I'll try and get that updated. Keep muted through the talk so we can hear from the speaker. And at the end, when we go to the questions, it'd be fantastic if we were able to jump onto video. But if not, no worries. And you can also drop a question in the chat and I'll try and pitch the question as well. So we get a chance to hear from everyone. Awesome. So thanks again for joining. We've got a really exciting talk today from Damanveer, who's at Arizona State University. He's done some really fascinating work tracking the distribution, partitioning, and transport of volatiles in planetary materials and the building blocks of planets. And we'll be hearing about some of that today, hopefully, and unlocking the origin of life-essential volatiles in rocky planets using iron meteorites. So thanks so much for taking the time to join us. And I'll stop sharing and hand over to you now, Damon.
Uh, Is my screen visible?
Yeah, it all looks good.
All right. Thank you for the invitation. So yeah, I'm very excited to share the recent work that I've been doing on the origin of three key life essential volatiles, primarily nitrogen, carbon, and water. Uh, most of our understanding on the origin of these three key life essential volatiles is primarily based on chondrites, these very primitive materials that existed very early in the solar system and sampled by some meteorites known as chondrites. But what I'm going to do today is I'm going to use a novel proxy that is iron meteorites to actually shed some new lights on this particular problem. And iron meteorites have been severely underutilized and underappreciated in this particular exercise. And what I'm going to try to convince you is that how using iron meteorites as a proxy to understand this particular problem is shed some new lights on our understanding and on the origin of life essential volatiles, and also challenges some critical astrophysical concepts, planetary science concepts, and so on and so forth. So with this, I'll go deeper into the talk. I'm very excited to take you all with me on this very exciting journey. So first of all, why are we interested in this particular problem, the origin of life essential volatiles? Earth is the only habitable planet that we know of in our solar system and beyond. In addition to the presence of sufficient liquid water, the composition of the Earth's atmosphere primarily composed of nitrogen and with trace amounts of carbon, plays a critical role in defining the habitability of the surface reservoirs of a planet. Also, nitrogen and carbon, along with water, are the primary components of the basic building blocks of life on a planet. Therefore, if we truly want to understand the habitability of a planet, we need to understand the origin of these three life-essential volatiles on the present-day surface reservoirs of a planet. But we also know that Earth is a tectonically active planet, which means that over billions of years of Earth's history, the exchange of volatiles between the Earth's interior and the superficial reservoirs controls the abundances of the volatile elements on the superficial reservoirs of a planet. Therefore, we truly want to understand the origin of volatiles on the surface reservoirs of a planet. We need to track the origin of volatiles in this big box over here termed as the bulk silicate Earth, which comprises of the Earth's mantle, crustal, atmosphere, ocean reservoirs. And core is thought to be an isolated reservoir, does not exchange a lot of materials over billions of years of Earth's history. So if we truly want to understand the origin of volatiles on the surface reservoirs of a planet, we need to track the origin of volatiles in this big box, again, the bulk silicate Earth. So the origin of volatiles in the bulk silicate Earth is generally tracked by comparing the isotopic composition of the volatiles in the bulk silicate Earth, represented by this red star over here, with some other cosmochemical reservoirs. So you have over on the y-axis the nitrogen isotopic composition represented in parts per mil. So your nitrogen isotopic composition of a sample divided by some standard and normal and multiplied by some factor over here. On the x-axis, you have the hydrogen isotopic composition. So the first thing we see in this plot is the nitrogen and hydrogen isotopic composition of the bulk silicate Earth is distinct from the nebular gas as well as from the cometary reservoirs. And if you look closely, the nitrogen and hydrogen isotopic composition of the bulk silicate Earth is broadly plots in a similar range as that of different classes of chondrites. So this has been used to argue that the first formed planetesimals in the early solar system sampled by these chondrites and the bulk silicate Earth have common origin of volatiles. But it's important to note that it's not an exact match for given class of chondrites. It's just plots in a broadly similar range. But if you look at the abundances of volatiles in the bulk silicate Earth normalized through primitive chondrites, we see that the volatiles in the bulk silicate Earth are extremely depleted. Carbon is depleted by 2 orders of magnitude, nitrogen by 3, hydrogen by 1.5 to 2 orders of magnitude. So you have two contrasting observations over here. On one hand, you have the isotopes telling us there's a similarity of origin, but on the other hand, you see this extreme depletion. So how do we put these two contrasting observations together? So if you look at chondrites, these very primitive materials, they can be very simplified as sedimentary rocks, which are composed of several disequilibrium assemblages. So CAIs, chondrules, and metals are these high temperature components, and volatiles are not present in any of these reservoirs. And then there is this dark colored matrix which binds all these high temperature components together. And volatiles are actually present in this matrix component. Water is primarily present in the phyllosilicates, some of it is in the organics, and carbon and nitrogen are primarily present in the organics in this dark colored matrix. But if you look at a present-day planet like Earth, it does not look anything like that of a chondrite, because a planet on Earth is a differentiated rocky body comprised of core, mantle, and crustal reservoirs. So if you truly want to understand the origin of volatiles in the bulk silicate Earth, we need to track this journey from very primordial materials in the early solar system to the fully formed planets. And this journey can be represented by this very simple schematic over here, that in the very early stages of in the protoplanetary disk, you have a cloud of gas and dust, and the dust particles collapse onto themselves to form planetesimals. And if these planetesimals form early enough, they accrete a very important short-lived radioactive nuclide known as 26 aluminum. And 26 aluminum has a half-life of around 0.7 million years. So planetesimals that form within the first couple of million years of the formation of the solar system, they undergo large-scale melting and differentiation to form differentiated planetesimals, again comprising of cores and mantles. And then these differentiated planetesimals over long time scales form differentiated planetary embryos, and they collide amongst themselves to form large Earth-like planets. So if you truly want to understand the journey of volatiles in the rocky planets, we need to track the volatiles through this entire process of planet formation, which is, again, a series of very complex processes. So what I'm going to focus today on is the first couple of million years of the formation of the solar system, and tracking the fate of volatiles in these very early planetesimals during their formation and differentiation. And I'll try to convince you that if you understand these processes taking place very, very early in the solar system, you have a pretty good handle and you can make a very important predictions on the origin of volatiles in the rocky planets by tracking what happens in the very, very early stages of solar system formation. So I'm going to go through my arguments by asking two key questions. The first question, and both of these questions are going to be based on iron meteorites. The first question I'm going to try to answer is how can iron meteorites shed light on the origin of nitrogen and carbon in the earliest solar system planetesimals? And in the second part of the talk, I'm going to answer how can iron meteorites shed light on the origin of water in the earliest solar system planetesimals. So, okay, to answer the first question, let us look at a current understanding of the initial architecture of our solar system. So based on the nucleosynthetic anomalies of several non-volatile elements, it has been convincingly shown that meteorites sample two isotopically distinct reservoirs. So carbonaceous chondrites sample the outer solar system reservoir, and carbonaceous chondrites are more volatile rich, containing a lot of nitrogen, carbon, and water. And non-carbonaceous chondrites sampled by ordinary chondrites and ancetite chondrites sample the inner solar system reservoir. So if you look at the formation ages of chondrites, their accretion ages of the planetesimals they come from, their accretion ages are around a couple of million years of the formation of the solar system or later. But planet formation models tell us that the seeds of the rocky planets started to form right at the onset of solar system formation, and chondrite parent bodies probably accreted much later. So there is another class of meteorites that can come to a rescue in solving this problem, and these kind of meteorites are iron meteorites. So iron meteorites again sample both the inner and outer solar system reservoirs. And if you look closely at the accretion ages of iron meteorites, so they started to form almost at the onset of solar system formation. And even the accretion ages of outer solar system iron meteorites could also be much earlier. They could have also started to form right at the onset of solar system formation. So they are a very good proxy to understand primarily on what did the earliest planetesimals actually look like, and also could help us understand the compositions of the first form, the seeds of the rocky planets, if the seeds started to form really, really early in the solar system history. To answer what iron meteorites actually are, so iron meteorites are the remnants of the metallic cores of the first form planetesimals in the solar system. So you have the planetesimals that form really, really early. They inherit a very important short-lived radioactive nuclide again, 26 aluminum. Due to heat release by 26 aluminum, the planetesimal undergoes large-scale melting. And when you have large-scale melting, metallic phase starts to separate out from the silicate melt in, say, in a magma ocean-like stage. And these droplets start to segregate out to form the metallic core. Eventually, the core will crystallize, it will cool down, and then you would have planetesimals that would completely disrupt due to some collisions, and then you have iron meteorites sampling those cores. So the idea is these metallic droplets, they were formed, they were because they were exchanged, they were in exchange with the silicate melts at very, very high temperature. So you should be reaching equilibrium very, very efficiently. So the idea is that if you sample the core, if you know the partitioning of volatiles between the metallic and silicate reservoirs, you can use the iron meteorites as a proxy to say something about the bulk. What did the bulk planetesimal actually look like? So they are a very interesting proxy in that way. So you just looking at the core, you can say something about the bulk planetesimal itself. And another important point that I need to make over here is that if we look at Earth and Mars, they plot right in the inner solar system cluster. So this tells us that Earth and Mars and other terrestrial planets in the inner solar system were primarily made up of inner solar system materials, and they had very, very small contribution from the outer solar system reservoir. So the isotopes tell us that 96% of the Earth and almost all of the Mars was primarily made up of inner solar system materials. So for that, if the inner solar system planetesimals were the primary building blocks of rocky planets, we need to focus on the inner solar system iron meteorites, because they are a proxy to better understand the compositions of the first form planetesimals in the inner solar system. So if you look back, if you look at the accretion ages, of course, it started to form really, really early. So what the classical astrophysical models would tell us is that the inner part of the disk where these planetesimals should be accreting should be extremely hot. The temperature should be high, so high that you should not be condensing any volatile elements in the inner part of the disk. So the only things that you should be condensing is very high temperature components like metal and rock, and the volatiles should only be condensing in the outer regions of the disk. And as planetesimals are primarily made of solid materials, the expectation is that the inner solar system planetesimals, that the earliest forming inner solar system planetesimals should be primarily made of volatile free materials, and the outer solar system planetesimals should be relatively volatile rich. And in that case, if the first form planetesimals in the inner solar system are extremely volatile depleted, then you could explain the volatile inventory of planets primarily from outer solar system materials. So the idea is, if the first form planetesimals in the inner solar system did not accrete any volatiles, then the bulk planetesimals should be volatile free. And if you form cores within these planetesimals, they should also be very volatile free. That's one's expectation if this basic astrophysical model of an extremely hot disk is actually correct. So what do iron meteorites actually tell us? So if you look at iron meteorites right now, so if you look at the carbon and nitrogen and abundances in iron meteorites, if those models were correct, if the temperature of the disk was extremely hot, so there should not be any carbon and nitrogen present in the iron meteorites. But when we start looking deeper into the iron meteorite data, we see something really interesting. So over here, the red color symbols represents the inner solar system iron meteorites that come from the cores that come from the inner part of the solar system, and blue symbols represent the outer solar system iron meteorites. And what you see over here is that the inner solar system iron meteorites, they not only contain nitrogen or carbon, but in some cases they contain more carbon than the outer solar system iron meteorites. And this story holds true for nitrogen as well. So you have nitrogen, there's significant presence of nitrogen in the inner solar system iron meteorites. And to put these numbers in perspective, if you look at the carbon and nitrogen budget of the bulk silicate Earth, you see there is significant carbon and nitrogen present in the cores of these planetesimals. There's a lot of nitrogen, carbon present. So the inner solar system iron meteors, they not only contain nitrogen and carbon, but they contain significant amount of nitrogen and carbon. So the next question arises: what is the source of carbon and nitrogen in these iron meteorites? So to understand the source, people generally look at isotopic signatures. So the issue with carbon is there is very limited measurements of carbon isotopes in iron meteorites. There are several problems through which we have not been able to measure a lot of carbon in the iron meteorites. But for nitrogen, there has been a lot of data that have been collected over the last 30 or 40 years on nitrogen isotopes in iron meteorites. So over here, different symbols represents different groups of iron meteorites. So each symbol represents a unique iron meteorite parent body. And what you see in this particular plot is that even though the nitrogen contents might vary by orders of magnitude in a given group of iron meteorites, their nitrogen isotopic compositions plot in very, very tight clusters. There's not a lot of variations in the nitrogen isotopic signatures. But there is nothing more that we could, no more information that we can get from this kind of a plot. So what I thought is, okay, we know all these measurements. And if I take the nitrogen isotopic compositions of a given group of iron meteorites now and plot them as a function of the growth zones of these planetesimals, what do I see? And what I found over here was something really, really interesting. So what we see over here is that the nitrogen isotopic composition of the inner solar system iron meteorites is very different from the nitrogen isotopic composition of the outer solar system iron meteorites. So this tells us that the inner solar system iron meteorites not only contain nitrogen, they contain nitrogen from a source probably that was isotopically distinct relative to the outer solar system reservoir. So this tells us that the cores of the first form planetesimals in the inner solar system, they not only contain nitrogen, but the nitrogen source or the nitrogen isotopic signature is also isotopically distinct relative to the outer solar system reservoir. So this kind of hints us that there must be some volatile bearing reservoir that is present in the inner part of the solar system right from the onset of solar system formation. So now the next question arises is how do iron meteorites or the cores actually inherit this nitrogen? So the current astrophysical models are correct that the inner part of the disk is extremely hot, then the most of the volatiles in the inner part of the disk should be present in the nebular gas. So the idea is that in the inner part of the disk, the temperatures are so high that the volatiles are present in the nebular gas, and you're also condensing metal in the inner part of the disk. So can the exchange of volatiles between the nebular gas and the metal, can this equilibrium reaction, can it explain the nitrogen abundances in the iron meteorites? Because if this is correct, then the nitrogen in the inner solar system iron meteorites was primarily sourced from the nebular gas, not from solid phase that was existing in the inner part of the disk. So to understand whether this is correct, we have to do some thermodynamic calculations. So over here on the y-axis, you see the nitrogen solubility in the alloy, which simply means that the maximum amount of nitrogen that you can dissolve in the metal at a certain set of conditions. And on the x-axis, you see the partial pressure of nitrogen in bars. So what you see over here is that the partial pressure of nitrogen in the nebular gas is extremely low. And if you do some thermodynamic calculations, you see that the nitrogen solubility in the alloy by nebular ingassing is very, very small. Even if it's not diffusion limited, the nitrogen solubility is extremely small and is much lower than the nitrogen abundances in iron meteorites. So through this mechanism, through the ingassing of nitrogen in the nebular metal, you cannot explain the nitrogen abundances in iron meteorites. So the other possibility is that maybe the first form planetesimals in the inner solar system accreted some nitrogen-bearing materials, and some of the nitrogen released at very, very high temperatures during core metal differentiation, and some of the nitrogen can be partitioned into the core under those set of conditions. Because core metal differentiation now takes place at much higher pressure, so the nitrogen solubility in the core forming alloy is actually much higher. So theoretically, it's possible that nitrogen solubility in the core forming alloy during core metal differentiation has the possibility to explain the nitrogen abundances in the present day iron meteorites. But we also understand that during core metal differentiation, nitrogen actually fractionates between the metallic and silicate reservoirs. So to actually quantify the exact amount of nitrogen that can go into the core forming alloy, you have to track this partitioning of nitrogen between the metallic and silicate metals, because nitrogen solubility only tells you the upper limit. It actually does not tell you how much of it actually goes into the metal during core metal differentiation. And to predict those numbers, one needs to know this partition coefficient of nitrogen between metallic and silicate melt during the conditions applicable for planetesimal differentiation. So this number is simply the nitrogen concentration in the alloy divided by nitrogen concentration in the silicate melt. So if this number is greater than 1, then nitrogen has more affinity for the core. And this is experimental data that have been collected over last 4 or 5 years. And this experimental data tells us that if the conditions of core metal differentiation were much more oxidized, that if you have core metal differentiation taking place at relatively oxidizing conditions, nitrogen acts as a siderophile element. And if the core metal differentiation in the first form planetesimals took place in more reduced conditions, then you cannot put a lot of nitrogen into the core. And now I'm going to talk about in the second part of the talk, we have very, very good estimates on the redox state of the parent bodies of iron meteorites, or under what sort of conditions core metal equilibration actually took place. And these conditions tell us is that the core metal differentiation actually took place at relatively oxidizing conditions. So now we know what numbers we need to use in these kind of models to actually predict the amount of nitrogen that can go into the core. And these models tell us that for realistic estimates, even for lower bounds of nitrogen that can be present in the interiors of planetesimals during core metal differentiation, you can actually indeed explain the nitrogen abundances in the iron meteorites or in the parent cores through this kind of a mechanism. So what does this entire picture tell us? So this kind of tells us that if there is nitrogen that goes into the core during the core metal differentiation, then the parent planetesimals should be accreting some nitrogen-bearing solids. So basically, if you have the if the planetesimals themselves were accreting some nitrogen-bearing solids, then those nitrogen-bearing solids should exist in the planetesimal forming region of the inner part of the disk. So what this tells us is that some nitrogen-bearing solids existed in the inner part of the disk right from the onset of solar system formation. And if you look at from the chondritic record, the primary carrier of nitrogen is generally organics. And if nitrogen was present as well, and if organics were the primary carrier of nitrogen, then the planetesimals should also be then the organics should also be delivering carbon to the first form planetesimals in the inner part of the solar system. So this kind of hints us and tells us that organics were predominantly very prevalent in the inner part of the disk right from the onset of the solar system formation. And as organics are very thermally unstable phases, it calls into question the thermal structure of the disk itself, whether the inner part of the disk was so hot that if the inner part of the disk was so hot, then you should not be having any organics and any solid organics in the inner part of the disk at the onset of solar system formation, because they could be completely destroyed. So what does it tell us? So now we know that the first form planetesimals in the inner part of the solar system, they accreted nitrogen and carbon, which kind of hints us at the possibility that there were nitrogen and carbon bearing organics that existed in the inner part of the disk right from the onset of the solar system formation. What does it tell us about the origin of nitrogen in the Earth? So if you look at the nitrogen isotopic composition of the Earth's mantle, it is very similar to that of ancetite chondrites. So ancetite chondrites are primitive meteorites that come from the inner part of the solar system. So this argument has been used to argue, that has been used to show that the nitrogen isotopic composition of the Earth's mantle could be explained by the accretion of only ancetite chondrite-like materials. You do not need any contribution from outer solar system materials. But what iron meteorites tell us is that the nitrogen isotopic variation in the inner solar system planetesimals is actually much, much larger. And the values of the nitrogen isotopic composition is actually much more negative. And if this is correct, and if these kind of planetesimals were the primary building blocks of Earth, then you need some contribution from outer solar system materials to explain the nitrogen isotopic composition of the Earth's mantle. So with this, I've answered the first part of the first question that I raised in the talk, is that the earliest inner solar system planetesimals actually inherited some locally sourced nitrogen and carbon, and Earth also retains the memory of that particular nitrogen and carbon. And also, it also tells you something about the dynamics of the planetary growth, that contribution of some 15 enriched materials, probably from the outer solar system, is necessary to explain the nitrogen isotopic composition of the Earth's mantle. So I have primarily focused on nitrogen and carbon until now in this particular talk, and I have not said anything about water. So how can we track the story of water in the early solar system planetesimals using iron meteorites? So I have some bad news for you, that we actually cannot directly measure hydrogen in iron meteorites. So the story is not as simple as nitrogen and carbon, because you could directly measure nitrogen and carbon in iron meteorites, and you can have some basic understanding on the origin of volatiles directly based on iron meteorites. But for hydrogen, the story is not as simple, because the measurements are very difficult. Hydrogen is nominally a lithophile element under nominal conditions of poor mental differentiation in planetesimals. So you have to go through some convoluted logic to actually come back to answer this particular question. So to answer this particular question, we have to take a step back and try to understand the mechanism of planetesimal formation in the disk itself. So the general idea is that what we believe right now is, to form planetesimals, you have to have regions in the disk where you have high dust-gas ratios. So in a nominal dust-gas ratio of the disk, you cannot form planetesimals. You need to artificially enhance some dust-gas ratio in the disk to actually form planetesimals. And the snow lines of major components of the building blocks of rocky planets could be one of the regions where you could actually increase this dust gas ratio. And water snow line is one of those regions where you could do that. So it has been shown by Joanna and others over the last few years that if you have ice-bearing pebbles migrating inwards to the star in the very early stages of in the disk. And as soon as they cross the water snow line, these ice-bearing pebbles fragment, and as they fragment, they lose some radial velocity. You can create some sort of a traffic jam at the water snow line. And also, you could have diffusion of water vapors and towards the outer part. So you can also increase the dust gas ratio in these. So if these water vapors condenses over here, you can again increase the dust gas ratio. And also, these ice-bearing pebbles have higher sticking efficiency. So all these mechanisms actually tell us that planetesimal formation could actually be very prevalent at the water snow line. It's very relatively easy to form planetesimals at the water snow line. And this kind of mechanism has been very nicely shown by Tim in a paper over a few years ago, where he showed that the water snow line could be the region where you could be forming planetesimals both in the inner and outer part of the disk. So during the build-up stage of the disk, during the viscous expansion of the disk, the water snow line kind of moves outward, and you have the formation of the first inner solar system planetesimals in the outwardly migrating snow line. And as the water snow line migrates inwards again, you can have the outer solar system planetesimals forming over these time scales. So basically, you have the first form planetesimals in the inner part of the disk and on the outer part of the disk, both forming at the water snow line. So what this argument is based on, that there should be some relative differences between the accretion ages of the inner and outer solar system iron meteorite parent bodies, because the inner solar system iron planetesimals should form earlier, and the outer solar system planetesimals should form later. And this idea was challenged in the same year or the next year by a couple of papers, where they actually showed that probably the planetesimals started to form, both the inner and outer solar system planetesimals started to form almost at similar timescales, and they predicted that based on some tentative evidence on the oxidation state of iron meteor parent bodies, that the first form planetesimals in the inner part of the solar system should actually accrete at the silicate sublimation line, and the outer part of the solar system, these planetesimals should be accreting at the water snow line. Again, two distinct regions in the disk, where Tim's model was they form in the same region of the disk. And the important point to remember over here is the water snow line, the condensation temperature is extremely low. So basically you have very low temperatures. And if you have silicate condensation line, the planetesimals should be accreting materials that are extremely volatile depleted because they're forming at very, very high temperature regions of the disk. So let's go through some thought exercise on what does this mean on the general compositions of the first form planetesimals in the inner solar system, if these ideas are correct. So there are certain kind of elements that one can track through this kind of a thought exercise, and those elements are highly siderophile elements. And highly siderophile elements means that as soon as core mental differentiation takes place, all these elements actually efficiently partition into the core. So I'm assuming two n-member scenarios over here. On the first left-hand scenario, you have a larger core, and on the right-hand scenario, you have a smaller core. So if everything being same, if you form a larger core, the concentration of highly siderophile elements should be lower. And if you form a smaller core, the concentration of highly siderophile elements should be higher. It's primarily if you throw a color in a larger pool, it would be more diluted. And if you throw some color in a smaller water pool, the colors will be more concentrated. So that's the basic idea. So if you have larger cores, you should have lower concentration of highly siderophile elements. And if you form smaller cores, you should have higher concentration of highly siderophile elements. If you form larger cores, of course, you should have more iron that needs to go into the core. And if more iron goes in the core, there is less iron, oxidized iron in the mantles of these planetesimals. And if you have formed smaller cores, you should have less iron in the core because cores are primarily made up of iron, and which means that you have more oxidized iron in the mantles of these planetesimals. So on the left-hand side, the story would be correct if you form cores under more reduced conditions, because if you have more reduced conditions, then more of the iron is present in the form of metallic iron, and it would go into the core. And if you form cores under oxidizing conditions, this is what you should be getting. And generally, water is thought to be the more prevalent or the dominant oxidizing agent in the early part of the solar system. So these reduced planetesimals should also be water poor, should be creating water poor materials, and the oxidized planetesimals should be creating more water rich materials. And this is actually indeed correct if we look at the iron meteorite data. If you look at the iron meteorite data, these are the characteristics that we see. And if you look at the outer solar system iron meteorites, these are the characteristics that we see. So this is what it hints at, that maybe the inner solar system planetesimals, earliest planetesimals in the inner solar system are probably more reduced than their outer solar system counterparts. But the idea is, if you look very closely at the predictions made by the silicate condensation line, the temperatures have to be extremely hot. And if the temperatures are extremely hot, then the inner solar system planetesimals should be accreting almost water-free materials, which would also indirectly mean that you should not have any oxidized iron in the mantles of these bodies, because most of the iron is actually is oxidized through these oxidation reactions with water. So what do we see from the iron meteoritic record? This could have been a very simple problem to solve if we were sampling the mantles of these first form planetesimals in the in the earliest part of the solar system. Because if you could look at their oxidation state, if you could measure their FeO contents, we could directly test these particular models. But it's not as simple, because we do not sample the mantles of the first form planetesimals in the solar system. We don't know the reason, but we only sample the cores of these iron meteorites. We don't sample their mantles. So the story is much more complicated than that. So then we have to again make up a new proxy to actually solve this problem. And then we're looking at three elements right now. Two of them are major elements in cores, and one is a trace element. And those elements are iron, nickel, and cobalt. And the interesting thing about iron, nickel, and cobalt is they're very, very similar volatility. So they cannot be fractionated by any volatility-related process. But the interesting thing is that nickel and cobalt are actually much more siderophile than iron. So at any kind of core mental differentiation conditions, nickel and cobalt actually efficiently partition into the cores of these planetesimals. So what you should have is that once you start with the planetesimal and eventually form a core, the cobalt by nickel ratio of the core should be identical to the cobalt by nickel ratio of the bulk, because all of the cobalt and nickel go into the core. But the thing about iron is, if the core mental differentiation takes place at more reduced conditions, then iron can efficiently partition into the core. And under those set of conditions, the iron-nickel ratio of the core should be equal to the iron-nickel ratio of the bulk. And this you should be expecting if the planetesimals are forming at the silicate condensation line. But if the planetesimals were accreting at the water snow line, they should be relatively more, or at or beyond water snow line, they should be accreting more water-bearing material. So they should be much more oxidized. In that kind of a case, not all the iron goes into the core. So some of the iron actually retains in the mantles of these planetesimals. So in that kind of a case, the iron-nickel ratio of the core should be lower than the iron-nickel ratio of the bulk. So now let us look at the iron meteoritic evidence and let's see what iron meteorites actually tell us. So if you look at the cobalt by nickel ratio of the iron meteorites, so these are the cobalt by nickel ratios, the numbers are very similar to that, or very close to 1. So there is very limited fractionation of cobalt and nickel during these kind of processes. And this is expected what we see based on theoretical predictions. But what we see based on the iron nickel ratios, we see something really, really interesting. So as expected, the outer solar system iron meteorites, they have lower iron nickel ratios. Their cores have lower iron nickel ratios than the inner solar system iron meteorites. And that is kind of expected because you should be expecting them, they should have more oxidized iron. But if you look at the iron by nickel ratios of the inner solar system iron meteorites, they're also consistently lower than 1. So this kind of tells us there is some iron that is missing in the cores, or there is some iron that was retained in the mantles of these bodies as oxidized iron. So how do you quantify the amount of iron that was actually left over in the mantles of these planetesimals? So you could do this by a very simple mass balance equation where you can track how nitrogen goes from the bulk and partitions between the core and mantle. But there are two unknowns in this particular equation, and you cannot solve this particular problem because we don't know the amount of iron in the core and we don't know the mass of iron in the mantle of these bodies. But if you track nitrogen simultaneously with iron, you can actually solve these equations. So the reason is because nitrogen is such a siderophile element under nominal conditions of core mantle differentiation, you could assume this number to be approximately 0. Then you can divide these equations. And the iron by nickel ratio of all planetesimals, if you look at the inner and outer solar system planetesimals, they're very, very consistent. It's very similar to the nebular signature. So you can track this iron by nickel ratio of the bulk planetesimals of the iron meteor parent bodies directly from chondritic numbers or even from solar nebular numbers. We know the iron and nitrogen concentration in the core. So the only unknown that we have is the iron that we need to constrain now is the mass of iron in the mantle. And what we found over here is something really interesting that, of course, the outer solar system iron meteorites, their parent bodies, they contain a bunch of oxidized iron. But even there is significant amount of iron that was present in the mantles of the first form planetesimals in the inner solar system. They contain a lot of oxidized iron. So if you look at these numbers, if you look at the nebular gas was extremely reduced. And if the nebular gas was extremely reduced, then and if there was no, and so basically most of the iron should be in the nebular gas. If you're condensing metal from the iron from the nebular gas, it should be present only in the form of metal. But if you look at the redox state or the oxygen fugacity of the first form planetesimals in the inner solar system, their FO2 is approximately 3 or 4 orders of magnitude higher than the nebular gas. So the question arises, how do you create that amount of oxidized iron in the mantles of these planetesimals? This could be generally explained because iron is such a dominant component, it's a major component in the planetesimals. So you need, and the oxidizing agent that you need should also be a dominant component that should be treated by the planetesimals. So if that could be explained if the first form planetesimals were accreting from ice and rock, and you basically have 26 aluminum decay, and when you have 26 aluminum decay, these planetesimals, when they accreted, they were highly porous and they have very high porosity and permeabilities. And if you melt ice, then the water can react with some metallic components and oxidize iron during this percolation or free percolation of fluids in these planetesimals. And you could write this simple kind of a reaction, like iron plus Fe plus H2O, to quantify the minimum amount of water that you need to oxidize, to explain the FeO abundances in the first form planetesimals in the inner solar system. And this tells us that the water abundances in the inner solar system iron meteorites are pretty significant. In the first form planetesimals in the inner solar system, this is the minimum amount of water that is needed to oxidize iron, because most of the iron most of the water could have actually freely percolated out from the system, because the system is an open system. It's moving out very freely. So the actual water contents accreted by the planetesimals in the inner part of the solar system could have been much, much higher. This is the minimum bound that you actually need. And these numbers are very similar to the water contents that you could be predicted from ordinary chondrites that formed in the inner part of the solar system. So this tells us is that the first formed planetesimals in the inner part of the system, inner part of the solar system, were probably accreting water-bearing materials. So this comes back to what is the astrophysical setting through which you can explain this kind of a mechanism. Is it the two-step migration of the water snow line as you go from the one time out inward and outward migration of the snow line? But we also know from astronomical and astrophysical models that the water snow line could be it could be very dynamic if you have the accretion rate to the stars that are varying. So the water snow line could move in would fluctuate in the disk because of the large scale temperature fluctuations in the disk, and the migration of the water snow line could actually seed planetesimals both in the inner and outer parts of the disk. Or probably these water-bearing planetesimals, these oxidized planetesimals, were accreting beyond the water snow line in the inner part of the disk, in a very special region of the disk. Again, these are all very tentative ideas. This is what our data actually kind of hints at. We don't have a solution for this particular problem right now. So now if we take a step back and look at the statistical representation of the oxidation state of the planetesimals in the solar system, what we see over here is that enstatite chondrites, obrites are extremely reduced as the nebular gas, and they are almost water-free. They do not contain any oxidized iron. But all the other planetesimals in the inner solar system, we have multitude of planetesimals. They are all very, very oxidized relative to enstatite chondrites and obrites. So probably enstatite chondrites and obrites, they were accreting in a very, very special region of the disk, in the innermost part of the inner disk, accreting by some very different mechanism, and they were accreting very reduced, very water-free materials. And all the other planetesimals in the inner part of the solar system, they were very oxidized. So there was widespread presence of oxidized planetesimals in the inner part of the solar system. And if you look closely at the oxidation states of planet, only Mercury has an oxidation state that is very similar to enstatite chondrites and obrites. And if you look at the oxidation state of all the other planets in the inner solar system and the moon, their oxidation states are very, very similar to these of the oxidation state of all these planetesimals in the inner solar system. It also brings down to the question that people generally believe that Earth, probably initially people thought that the mantle abundances of all the siderophile elements could be explained if the Earth initially accreted from more reduced materials and finally accreted more oxidized materials. But if there is widespread presence of oxidized planetesimals in the inner solar system, probably it is possible that the oxidation state of the building blocks of rocky planets did not vary by quite a bit. They were all very consistent. Again, there are a lot of assumptions in these core formation models. We have to go back and track this problem again. But this kind of tells us that there were oxidized planetesimals, there were water-bearing planetesimals, and probably they were contributing significantly to the formation of rocky planets. So again, I'm going to end it over here. That this kind of tells us is that if you look at this first form planetesimals in the inner solar system, they actually tell us and reshape a lot of our understanding that the first form planetesimals in the inner part of the solar system, they were accreting nitrogen, carbon, and water-bearing materials. Probably the inner part of the disk was not as hot as expected, that these volatiles should be present very commonly in the planet forming region of the disk. And what this tells us is if the volatiles were present in the building blocks of rocky planets, then if you finally want to understand the origin of volatiles in the rocky planets, you need to track each and every step of the planet formation sequence now to understand the volatile budgets of rocky planets. You cannot go that, the seeds were volatile free, and then you could be delivering volatiles at a much later stage. You need to track each and every step of the planet formation sequence right from the onset of solar system formation to track the volatile budgets of rocky planets. And with this, I'll leave with two key take-home messages: that the earliest planetesimals in the inner solar system likely accreted nitrogen, carbon, and water-bearing materials. And what this tells us is the volatile inventory of the Earth and other rocky planets in the inner solar system was shaped by processes taking place during their entire accretion history rather than during the late stage processes. Thank you.
Awesome. Thanks so much. That was a really fantastic tour through the volatile history of the early solar system. So we've got time for questions, which is fantastic. So if you want to ask a question, as before, you could put your hand up. We can call you forward and you can ask it live, which would be fantastic, or you can drop it in the chat and I'm happy to ask it as well. we'd like to ask one question to get us started, which is the nitrogen isotopes. I think you showed a figure that emphasized how fractionated the nebula gas was from solids in terms of its nitrogen isotope composition. I mean,
Yeah.
is there the potential for fractionation processes to explain the differences between like nitrogen isotope fractionation processes to explain the difference between objects, which just sort of coincidentally is aliasing in radial distance?
Okay. So are you talking about this plot over here that you have these variations in nitrogen isotopic signatures in meteorites?
Yeah.
Let me just pull up this plot. Okay.
Yes. Yeah, that one.
Which one? This one over. Okay. Let me go back. Yeah. Okay. So I think if this plot over here, right?
Yeah, so I mean, just basically, it's kind of to what extent is the nitrogen isotopes actually tracking source characteristics versus, a process which is fractionated nitrogen isotopes, because nitrogen, the isotope fractionation is, or the isotopic signature is quite different to that of the classic observation of, the MCCC dichotomy, which is
Right.
rooted in isotopes, which are, anomalies which are nucleosynthetic in origin.
Yeah, I think, okay, I think this is a very interesting, I think, I think this is a very important question. And what I want to say over here is that actually, I simplified the story over here, and I do believe right now that it's actually not a source signature. It actually is it's a planetesimal, it's a, let me actually just show you a plot. I think it will probably help me explain this in a much more simpler manner. So, okay. All right. So basically, if you look at this plot over here, so basically what we earlier thought is that if you measure some nitrogen isotopic signature in a chondrite, and then you can say something about the bulk planetesimal itself, like but now if you look at the nitrogen contents of the chondrites as a function of the peak metamorphic temperature, so what you see over here is different classes of chondrites coming from different regions of the disk, but they plot on a common geophysical, so they plot on a common scale. So basically, this tells us that common geophysical processes are actually affecting their nitrogen isotopic signature. So basically, most of the nitrogen is present in the thermally unstable components of chondrite. So basically, it's the soluble organic matter, which is very, very susceptible to alteration processes. And at very, very low temperatures, you lose this component. And as you lose this component, the nitrogen isotopic compositions also begin to evolve. And actually, now we are working on a paper where we are actually quantifying the exact isotopic fractionation involved with these kind of mechanisms. And then you eventually shape up to lower nitrogen isotopic composition values. So the interesting thing that we see over here is that in the inner part of the solar system, we only have planetesimals which have seen higher peak metamorphic temperatures. So you only have nitrogen isotopic compositions of chondrites that have more negative values. And from outer solar system, we have planetesimals that have higher delta 59 values or have experienced lower peak metamorphic temperatures. So basically, so what this kind of tells us is that it's not a source signature. Probably the materials that were accreting both in the inner part and outer part of the disk, they were accreting common materials. And the nitrogen isotopic signatures that you eventually see are shaped by these planetesimal scale processes that are actually taking place over here. So I simplified that argument in the talk over there because I didn't want to go into the complexities of these arguments. But actually, I do believe right now it's actually not a source signature, but it's a fractionation signature for nitrogen, for carbon, as well as for hydrogen. So that's why I think it's imperative that we do not take the geochemical values of chondrites that are measured on face value until and unless we put them in a geophysical context and actually understand what those values mean. Because what you can have over here is that you could have chondrites that are coming from the same planetesimals from different regions of the planetesimals and experiencing different peak metamorphic temperatures, and they could be representative of these values from different regions of the planet. So I think until and unless we have this, I think there's going to be a lot more work that we are working on right now to actually quantify these processes as a function of temperature, and then I think we'll actually get deeper into this particular problem. But it's
Yeah,
definitely not a source signature.
cool. Yeah, that makes a lot of sense. Thanks so much. Any other questions? Cool. Yeah, we've had a question in the chat from Behav. Apologies if I mispronounced your name. Thanks for the great talk. You mentioned nitrogen isotopic signatures suggest a transfer of nitrogen reservoirs from the outer solar system to the inner regions. Can you comment on the processes that can lead to such a transfer?
Think probably the migration of gas giants. So you basically have to change so I think probably the migration of the gas giants could be one of those processes that could infiltrate the outer solar system materials to the inner solar system. And not only based on the nitrogen isotopic signatures, if you look at the other isotopic signatures from molybdenum isotopes, they also tell us that during the last stages of planet formation sequence, you have some infiltration of outer solar system materials to the formation of the Earth. And it's probably related to the migration of to these gas giants.
And you've kind of put all the work in the paradigm of planetesimals and planetesimal processes. Is there any tension between that and a model of planetary accretion that focuses on the accretion of smaller objects like pebbles, or which won't have had the same thermal processing history, and so you sort of accrete juvenile material without this pre-processing?
Yeah, so I haven't put my the data. I think these on those kind of a context. I think at face value, I don't think we can actually deconvolve those features right now, whether like the planet formation is through a pebble accretion process or not, because the thing is with these volatile signatures, until and unless we understand the planetesimal scale processes and what do those signatures actually even mean, like what are the absolute numbers, what are the nitrogen carbon isotopic signatures they even mean, it's very difficult to uh, take a step back and look at the source signatures and so on and so forth. It's complicated as of now.
Yeah. Yeah.
And we don't have a third isotope for these elements. That's also a major problem. If we had that, that would have made things much more simpler.
Yeah, absolutely. Always wish for more isotopes. Fantastic. Gopalan, got a question.
Hi, thank you very much. It was a nice talk. I just wanted to understand about the diversity of nitrogen isotopic composition within the iron meteorites that are presumably formed in the inner solar system. You showed a diagram.
I think probably we can go in here. Would that?
Yeah, and there was another one where you tried to show that how they range and how the Earth's composition is slightly more. Yeah, if the Earth is taken as zero, the diversity of the inner solar system iron meteorites goes up to -100 per mil. So on the positive side, the material that has formed in the outer solar system is consistently positive. So does that signature, is there a reason why there is this kind of a dichotomy in your view?
Okay. When I published this 2020 paper in 2021, I thought it was source signature. That was my idea back then. I thought it was a source signature, but then I had a paper in APJ a couple of years later, where you actually kind of find out it's actually not, probably not at least for the chondrites, it's not a source signature. It's probably a like a fractionation signature in the planetesimals themselves.
Yes.
But then iron meteorites actually are a problem in that kind of a setting, because what you should be expecting is, because iron meteorites, the nitrogen that goes into the iron meteorites, it should be a high temperature component. And if it is a high temperature component, it should also be showing negative signatures. But all the iron meteorites that come from the outer solar system, they consistently have positive numbers. So a problem I thought that I had solved, I think that is unsolved now. I don't know the reason very well. Chondrites, I can actually explain very well with my models right now with the quantification of these numbers, especially like if you look at these iron meteorites over here, the 2Cs, they don't show any mass-dependent isotopic fractionation signatures, but their delta 15N values are very high, and their values are as high as the most primitive components we see in the CR chondrites or the Bell's chondrites. That's one. And there are others. And also we now have ungrouped irons that also plot in this kind of a range. So that's also kind of very, very interesting. So what we see in chondrites is that generally the 15N rich components are also the most are the components that are most prone to any kind of alteration process. But somehow in iron meteors, you retain those. Like, I don't have the answer. So, and I
Okay.
thought I had solved this problem, but I just don't know right now.
Okay. Okay.
Yeah.
Okay.
But for chondrites, I definitely believe that you can very, very nicely explain. I think we now have a quantification. We are working on a framework where we're quantifying these numbers. With chondrites, you can very nicely have a very quantitative framework to actually explain those signatures, that this variation as a function of temperature. But iron meteorites, I don't know.
Fantastic question.
Can I ask
you
one
wanna-
more question if there is time, or somebody else has?
yeah, go for it. But if anyone else has a question, please put your hand up or drop something in the chat.
Thank you. I liked the way you have used the cobalt by nickel ratio and iron by nickel ratio as a proxy in the mantle versus the core as a proxy for water content. Now, is there any situation where this kind of a proxy may not work? And do you anticipate it to work across the spectrum?
Actually, I think this proxy works superbly well, because I think I'll just go back to that plot again. Let me
Okay.
just, okay. So these are these solid numbers. So I have quantified the oxidation states over here by two different proxies, by the iron nickel ratio proxy and the iron cobalt ratio proxy. They show some variations.
Right.
But then there are numbers in iron meteorites that have been measured by other proxies. So basically the 4As, these has been measured before by Andy Campbell a few years back by looking at the trace element signatures. And this was measured based on the chromium abundance in iron meteorites. So they very well correlate. And then we also have idea about the non-magmatic irons. So if you look at the non-magmatic irons over here, so in the non-magmatic irons, you can measure, because there are the silicate reservoirs. And if you look at the non-magmatic irons over here, their numbers are also very, very similar to what we have over here. And then we also looked at an ungrouped magmatic iron. So all of them, they give us very, very identical numbers. And even for 4As, we also have some iron meteorites for which we have the silicate reservoirs. Again, we see very oxidized signatures. So I think that proxy is, I think, pretty solid right now.
Okay.
And another important thing is, if core metal differentiation was taking place at relatively reduced conditions, say somewhere over here, then there's another important trace element that starts to go into the core, and that element is silicon. And people have tried to measure silicon in iron meteorites, and they have never been able to measure silicon beyond very, very low few ppm numbers. And if you had core metal differentiation over here, you should be expecting a bunch of silicon that goes into the core. So there's a lot of different proxies that tell us the same answer.
Okay.
Yeah. So I think this proxy is pretty solid on that sense.
Thank you.
Fantastic. Yeah, thanks for those questions and for drawing out remaining mystery. It's always good to see there's more work to be done. That pretty much brings us to the close for today. So thanks everyone for joining, and thanks very much for the questions and an interesting kind of discussion and clarification on some of these ideas. It's been really good. Before thanking the speaker again, just to point out that we've got a talk next month at the usual kind of first Thursday, so 4th of June. That'll be 1 p.m. UTC, so kind of a bit earlier. And that's from Anna Mittelholtz on Mars's magnetic field, progress and puzzles. So kind of linked in some senses to what we've been hearing about core formation today, but now at the kind of planetary scale. So that would be great. So thanks again so much, Damon, for the talk today. Really, really fantastic collection of work, creating a really great, coherent story, which I really enjoyed. And thanks also to Lynn Bolt Christmas, who's been running the technical host today. So thanks so much for helping with that as well. Thanks, everyone. Take care.